Hello everyone and welcome to another lesson. Professor Mab here. The topic of today's lesson is stress element and stress transformation. This topic is part of the following courses: machine element design and strength of materials. The stress element is considered a small part of a body in form of a cube with stresses acting on its 6 faces. You can see 3 faces in this figure. The stress state in a 3-dimensional body can be described by the following 9 components: sigma x, sigma y, and sigma z. Tau xy, yx, xz, zx, xi, and yz. First, we're going to do a quick review of these stress components in this lesson. There are 2 types of stress: normal stress and shear stress. Normal stress acts normal to a surface and tends to either pull out the surface, tensile, or push it in, compressive. Tensile stresses are positive, while compressive stresses are negative. All normal stresses shown in this figure are tensile. Shear stress acts parallel to the faces of the cube in pairs or couples on opposite faces. A shear stress pair, for example, tau xyi and tau yx, tends to distort the cube into a rhomboidal shape. For shear stresses, the first subscript indicates the direction of the surface normal vector. For example, in tau xy, x is the direction of the surface normal vector, which is this surface having a normal vector in the plus x direction. The second subscript indicates the direction of shear stress. For example, in tau xy, y is the direction of the stress, which is in plus y direction. The sign convention for shear stress is it is considered positive if the surface normal and the stress direction have the same sign, and negative if the surface normal and a stress direction have different signs. For example, tau xy in this figure is positive since its surface normal vector in plus x direction and the stress direction in plus y direction. Both have the same sign. In fact, all shear stresses shown in this figure are all positive because they are acting on the positive faces of the cube and their directions are also positive. So now that we have discussed all these 9 components, we can continue our analysis on the 3D stress element. Another important fact here is that due to equilibrium, cross shears are equal. So tau xy equals tau yx, and so on. This reduces the stress components from 9 to 6. A more simplified stress element is 2-dimensional plane stress, which occurs when stresses on one surface are 0. This reduces the stress components acting on the stress element into only 3: sigma x, sigma y, and tau xy. The good news is most design problems can be solved using the plane stress analysis. An important point to emphasize here is the stress element in plane stress is still a 3D cube, where stresses on one surface are 0. That's the surface facing the screen, and consequently, due to equilibrium, the stresses on opposite surface are 0 as well. But the stresses on the other 4 sides of the cube aren't 0 and shown in the figure. Sometimes in design problems, due to the direction of loading, we might need to change the orientation of axes when analyzing a stress state in a component. The stress situation at a point remains unchanged when we change the orientation of axes, but the stress components will have different magnitudes. Let's consider that the plane stress element is cut by a diagonal plane with a normal n at an angle phi counterclockwise from the x-axis. So we're trying to find the normal and shear stresses acting upon this diagonal plane, sigma and tau. To find sigma and tau on this diagonal plane, we need to balance the forces caused by all the stress components acting on the stress element. We do this in x and y directions. In x direction, the first term is sigma x in negative direction, and multiplied by the surface area that is acting on which is dy dz. Similarly, we write the other force components. We do the same for y direction. Now, we can replace the cosine phi with dy over ds and sine phi with dx over ds. To simplify, we divide all terms by ds dz. So these equations are simplified to the following. Now, if we multiply the first equation by cosine phi and the second equation by sine phi, we'll get. So we get these equations. And we're almost done. Now, if we add up these equations, it results in eliminating tau. So we can find sigma. So we find sigma, and in a similar fashion, tau, acting on the diagonal plane rotated by angle phi, counterclockwise from the x-axis, based on sigma x, sigma y, and tau xy. In previous set of equations, we only found the normal stress on one diagonal surface, x prime. Using the same procedure, we can find the normal stress acting on the perpendicular surface, y prime as well. So the general equations for transformation of a stress element from a set of coordinates, such as xy, to a new set of coordinates, x, yet rotated by angle phi, will be. These equations will help us to find at what orientation of the stress element the maximum critical stresses occur that might cause failure. Thanks for watching this video. Please let me know if you have any questions.